So hi everyone, welcome to our last talk of the semester. And again, in case there are some new audience here, this talk series will be given by the awardees of NCU-Delta Young Astronomer Lectureship, which was founded by the National Central University and the Delta Electronics Foundation to recognize young scholars who have made outstanding contributions in this field. So each year, the awardee will be invited to Taiwan and to interact with the local astronomers and the public. So I think the first award was given in 2012. And the original plan for this year was to invite all the previous awardees to come back to Taiwan. But unfortunately, we have to make this event online due to the pandemic. So our speaker today is Professor Stephen Smartt. I think Stephen received this award in 2012, which is the very first awardees of this lectureship. And now he's a professor in the Astrophysics Research Center at the Queen's University, Belfast. And he's a world expert, especially in studying the depth of massive stars and supernovae. And he has led many, I think, important projects such as Pan-STARRS in the Survey for Transient and PASTEL project, which has classified thousands of transients so far. I remember I was also part of that project, when I was a graduate student. I was also, just recently he has started another ambitious project called ENGRAVE, which is dedicated to follow up the electromagnetic counterpart of gravitational wave detections. So it's really our great pleasure to have him here. So today he's going to talk about the present and future of multi-messenger astrophysics. So just a few announcements before we start. Please mute yourself during the talk. If you have any questions or comments, you can leave them in the chat box anytime you want. We will try to come back to those questions in the middle of the talk or during the Q&A session after the talk. So, all right, Stephen, I'll let you take this away if you're ready.
Thank you, Yan-Chen, and it's a pleasure to talk to you. I'm just sorry I can't be in Taiwan this time. Hopefully, in the not too distant future, we'll be able to travel and I'll be able to make the trip there. But thank you for the opportunity to talk to you again. I'm going to talk about the present and future of multi-messenger astrophysics. It's an area which has just started really in the last few years. Yan-Chen suggested I give a very broad overview for the first five or 10 minutes and before I start my talk properly. So let me give you an overview of and I'm going to talk about some of the projects which are listed here that Yan-Chen mentioned, but let me just give you a general introduction to the transient sky and the new developments which have taken us beyond photons in detecting objects, transient objects in the universe. And beyond photons, I really mean gravitational waves. There have been detections of high energy neutrinos from the ice cube detector at the South Pole. I won't talk about those in this talk, but I'll focus on gravitational waves and combining photons with the detection of gravitational waves. I came to Taiwan back in 2012 and was fortunate enough to be given the award that Yan-Chen described. And most of my work at that time, up until the last few years, has been focused on the transient sky from the optical perspective. So finding extragalactic transients, mostly supernovae, but some which are unexplained, for which the physical mechanism to produce the luminosity does not appear to be or is difficult to describe with the normal supernovae mechanisms. That is core collapse in a moderately massive star, and a type 1a supernova, which is the destruction of a white dwarf. But here's a very nice movie put together by Isaac Shivers at UC Berkeley, and it shows the transient extragalactic sky from 1,000 years ago when humans first started observing and recording the transient sky. And these are all supernovae or supernovae-like transients in galaxies outside the Milky Way. And much of my work has focused on this in my career, and certainly the last 10 years. But the big developments in the last 4 years. Well, before I get there, just to point out that there are about 83,000. This was in July this year. I did this count. It's gone up significantly since, but there are about 83,000 known and recorded extragalactic transients from different surveys around the world that record their the objects that they think are true transients in outside our galaxy. Again, they're mostly supernovae, they're mostly the normal supernova population, and these are recorded currently by surveys such as ZTF, Pan-STARRS, the Gaia satellite, Atlas, which I have a significant involvement in, and Assassin, which focuses on the bright end of the supernova population. But there are about 83,000 optical transients registered with the IU and given formal IU recognition and names, and that's probably up to about 85 to 90,000 now. And so with these numbers, it becomes interesting to look at the extremes of the population, what objects we can find that don't fit the normal paradigms of supernovae, of core collapse of massive stars, and type 1a supernovae from white dwarfs. The universe's densest objects tend to drive, so this picture of the transient universe is driven by either the formation or the explosion of compact objects. So normal supernovae from massive stars form neutron stars. Their core collapses, and the core will form a neutron star, and that gravitational potential energy, which is released when the core collapses to form a neutron star, drives the explosion. White dwarfs produce type 1a supernovae when they become unstable and they shrink, their temperature goes up, and they end up in a thermonuclear runaway, and carbon and oxygen burns to radioactive nickel, which drives the explosion. And black holes are almost certainly formed in some types of stellar transients. Exactly which ones we don't know for sure. Probably in the formation of long gamma ray bursts and their associated supernovae. But there may be other transients that form black holes that we haven't quite identified yet. But these are the universe's densest objects, and these also produce, as we'll see, gravitational waves when they are in binary systems. But this densest form of matter, if we compare them just in a broad sense, white dwarfs have a density, so they are the size of the Earth, the radius of the Earth, and about 1.4 solar masses squeezed into the radius of the Earth. That's the most massive white dwarf. And they would have a density of 10,000 kilograms per centimeter cubed. So think of a teaspoon, and 1 teaspoon of white dwarf matter would weigh 10,000 tons. For a neutron star, that is similar sort of mass to a white dwarf, the maximum mass of a white dwarf, so about 1 to 2 solar mass, 1.4 to 2 solar masses. But that material is squeezed down into a 10-kilometer radius. That's approximately the radius of a neutron star. So that means the density of material, the amount of material on a teaspoon, is 6 times 10 to the 11. So imagine everyone on Earth squeezed onto a teaspoon. That's the density of neutron stars, the density of an atomic nucleus. And then black holes, well, we're not sure exactly what the form of matter is within the event horizon of a black hole, but if for an object which is greater than 2 solar masses, the black hole of something around 2 solar masses or greater would have a radius, a Schwarzschild radius of around 5 kilometers. So something which it would have an effective density higher than that of neutron stars. So it's the formation of these dense objects that really produce the transient universe. Either their formation produces a transient, or their destruction produces a transient. So the next, the recent development, very exciting development in this field was in 2015, when black holes, presumably produced by supernovae in some way, were detected by gravitational wave detectors, LIGO and Virgo collaboration. The first one was detected only by the LIGO detectors in the US. These were surprisingly very massive black holes, a 36 and a 29 solar mass black hole discovered in 2015, which were orbiting around each other, and their final in-spiral and merger was detected by LIGO. The whole event only lasted about 0.1 of a second, but it was an extremely loud and high amplitude event detected in the gravitational wave interferometers. The Nobel Prize was awarded for this in 2017, and this opened up a new window in the universe for us to combine the gravitational wave signatures with photons. The next big development in this field was just 2 years later in 2017. So several black hole mergers were detected between 2015 and 2017. And in 2017, then the first binary neutron star was detected at a surprisingly close distance of only 40 megaparsecs. At the time, a short GRB, a weak short GRB was observed, both by Fermi and Integral. And the spatial location of the GRB from triangulation of Fermi and Integral, combined with the sky map from the gravitational wave detectors, pinpointed this relatively small area on the sky, only about 40 square degrees, 30 to 40 square degrees. And what several teams around the world did, they looked in this area of sky and they picked out the 20 largest galaxies and searched those galaxies for any optical transient. And in one of them, NGC 4993, a distance of 40 megaparsecs, an optical transient was found that hadn't been seen before in surveys of the sky up to that point. Here's the host galaxy, and here is the source which created the gravitational wave. So this is the optical source pinpointed exactly to its host galaxy. This caused the gravitational wave GWA 17817. And this gravitational wave event from two merging neutron stars produced what we call a kilonova. And a kilonova is labeled because it's about 1,000 times more luminous than a nova. And this image was taken by Janet Chen with the Grand facility at ESO. And there you can see an object which started very blue and became red, which I'll talk a little bit more about. But this is pinpointing the first, for the first time, a source of gravitational waves. Two neutron stars merging, and only about 1 or 2% of the total matter was ejected, but that was enough to create this optical transient. It faded very rapidly. We've never seen anything like this before. It faded. It was reasonably luminous, but it faded very quickly over a period of 10 days. So that was 2015, detection of gravitational waves from merging black holes. 2017, detection of the first neutron star merger by LIGO and Virgo, and detection of the first kilonova associated with neutron star mergers. But that's now 4 years ago. So what have we learned and where are we going in this field? That's the end of my introduction for now. I'll just pause just to see if there are any questions. Yen Chen suggests that I pause a couple of times during the talk for any questions.
Okay. Any questions for Stephen? You can either type your question in the chat box or just speak up. Any questions?
No. Okay.
Nope. Okay, I think we're good.
Okay. So yeah, so I guess you're wondering now, with 4 years past, what has happened since? This was quite an amazing discovery, both with the signal from the gravitational waves, a very loud, very high amplitude signal from the neutron star merger, because it was at 40 megaparsecs. So in 2017, the neutron star merger really did get everyone quite excited that we could be at a stage where we'd be regularly combining gravitational wave detections with multi-wavelength detections, both from the gamma rays right through to radio. And of course, in 2015, just to highlight, that was the real start of this field. Now, the answer to what has happened since is really determined by the rates of these objects, the true rate of black hole mergers and neutron star mergers, and potentially neutron star and black hole mergers. So to give you an idea, the 2015 event from very high mass black holes was a very loud, high amplitude event in the gravitational wave detectors. You can see the data here, very high signal to noise in the these are the waveforms detected by the two detectors in Livingston and Washington in the US. I'm sure you've seen these many of these plots before. This was at redshift 0.1, 400 megaparsecs. In 2017, the neutron star event This was detected at 40 megaparsecs, factor of 10 in distance closer. Now, the black hole detections are much more common. It turns out the observed rate of black holes, well, LIGO and Virgo detect black hole mergers, and they did in the last run, in their last observing run, at a rate of about 1 a week. But within a distance of about 400 megaparsecs, there are about 5 black hole mergers per year. That's approximately the rate that LIGO imply, the true rate that they imply. So within that distance of 400 megaparsecs, there are 5 black hole mergers per year out to that distance. Many more beyond that at higher redshift, which LIGO Virgo are sensitive to, but within that fairly nearby volume of 400 megaparsecs, that's quite common. This event in 2015 is pretty common event, 5 per year. Maybe even a little bit, and maybe even a little bit more, which they will tie down in the next observing run. It turns out that the rate of neutron star mergers within 40 megaparsecs, the true rate of events like GW 170817 is only once per decade. So what I mean there is, neutron star mergers within 40 megaparsecs are probably once in a decade event. It means that this one was quite a rare event that we detected in 2017. So within 100 megaparsecs, for example, that's just slightly more than a factor of 2 in distance, which means it's nearly a factor of 10 in volume. The volume enclosed within 100 megaparsecs is about a factor of 10 greater than 40 megaparsecs. So we expect within 100 megaparsecs, 1 neutron star event per year. That's the estimated true rate from LIGO. So given this is 1 per decade, we don't expect to have, it's not surprising we haven't detected something like this in the local universe without a gravitational wave detection. Pretty rare within 40 megaparsecs. It turns out we were quite lucky. So this is what LIGO produced so far. This is their latest compilation of all the compact mergers, and you can see that nearly all of them, the vast majority of their events that they've detected are black holes. So this just plots the mass of any individual object within the binary system and the combined mass of the merged object. And they're mostly the 3 things that I think you would immediately notice about this plot is that there are lots of black holes above 20 to, in the regime of 20 to 50 solar masses that merge, and they're the loudest events in LIGO, so they tend to be overrepresented. There are only 2 events of which are neutron star mergers. So that's in 2017 and 1 in 2019, which I will show you. There does seem to be a mass gap between the neutron stars detected and the black holes. There are a number of events that are likely to be neutron star plus black hole mergers, quite asymmetric masses. You can see the neutron stars here are in orange and the black holes are in blue. So there are some which are likely neutron star plus black hole mergers. But there does seem to be a gap between the maximum mass that we expect from a neutron star, around 2 to 2.5 solar masses, and about 5 solar mass black holes. This is quite similar to the mass gap we see in the Milky Way and X-ray binaries. So it could be, it's not statistically significant yet, but there could be evidence here for the mass gap that's visible in the Milky Way compact objects. And that will probably become clear over the next 1 or 2 observing runs with LIGO, Virgo, and Kagra when they come online, or whether or not this mass gap really does exist in the binary mergers. So when I said, so down here in the bottom left is the representation of the GW 170817 famous event. 2 fairly normal neutron stars, about 1.3 solar masses, which merged together. The only other clear, definite neutron star merger that was detected since then was in 2019 in the 3rd LIGO Virgo observing run. And this one was at quite a larger distance, quite a significantly higher distance, 150 megaparsecs compared to 40 megaparsecs. So this one, so this is the the time versus frequency for the signal. So if I'm just, let's see if this works. There's a little movie here which you should see. You should see the source, the detection of the source flicking on and off. So what happens here is that as the neutron stars orbit around each other and their orbital radius shrinks, and the period decreases, the frequency goes up rapidly. So you can see that there is a signal here which rises in frequency. It's quite amazing that they picked out this signal within a few seconds, within I think 2 minutes of the merger happening. They were able to identify the signal automatically and send out an alert. The interesting thing about this object was the inferred masses of the two neutron stars are quite high. It's more massive than typical galactic binary neutron stars. So the gray histogram here at the top is the histogram of binary neutron stars in the galaxy, their masses. So combined mass is about 2.7. So imagine two neutron stars, about 1.3 solar masses each. The combined mass around 2.6, 2.7. That would be the median mass in the galaxy. This one had a combined mass of around 3.3. So two quite heavy neutron stars. So did we detect anything from this, any optical transient from this? So the answer is no, nothing, no optical transient or any electromagnetic transient was found for this event. And the reason may be is that the one half, it was only detected by one gravitational wave detector. The others were offline at the time, and they were not, well, one of the LIGO detectors was offline. Hanford was offline. Livingstone detected, and Virgo, this was too distant for Virgo to detect it, but it did have a non-detection. But half of the sky map, localized sky map, was in daytime. So we weren't able, no one was able to map out this half of the sky map, and it was very large because there was only one detection in one detector. Now that sky map, the 90% area was 7,000 square degrees. That's a significant chunk of the whole sky. ZTF mapped out most of the sky map, which was in darkness, which was available at night. And they mapped that out, which you can see here in the top left plot. We also observed this with both Atlas and Pan-STARRS based in Hawaii. We covered about 30%. I think ZTF covered about 50% of the sky map. No one detected any obvious transient associated with this object, but half of the sky map was in daytime, so perhaps not unexpected. We would have needed some good fortune to detect a transient from this source. And it was at 150 megaparsecs, so much more difficult than for 170817, a factor of 4 in distance, so a factor of 16 in luminosity, which is about three magnitudes fainter. So our detectors would have, the sensitivity of our surveys with ZTF and Pan-STARRS and Atlas would have been sensitive to detect something like 170817 at that distance. But we can't really say for sure that there was not an optical transient because of the size of the sky map and solar conjunction. Given that, so that's us up to date really with electromagnetic counterparts of gravitational waves. There has only been one. It was back in 2017. So now the two things I'll talk about for the rest of the talk are, is there anything more we can learn about the kilonova from 2017? And what are the prospects for the next run with the gravitational wave detectors, which will start in December 2022. So approximately 1 year from now. The LIGO, Virgo, and Kagra are hoping to start their 4th observing run, which will last approximately 1 year. So what more can we learn about the data that we have for the kilonova, which we call AT for astronomical transient 2017 GFO, which is the same object that produced the gravitational wave event and the GRB 170817, the weak short GRB. And this is a light curve on the right showing you how quickly this object faded. So within 10 days, you can see this faded by a factor of 100. Log L went from 10 to the 42 ergs per second. So the luminosity of this event, total bolometric luminosity of this event, decreased from 10 to the 42 down to 10 to the 40 in 10 days. So a factor of 100 decrease in 10 days. That's a very fast decline, but it's consistent with only about 0.02 solar of ejecta, which is expanding at about 0.2 or 0.3 C. And it's if you put in a model of radioactive heating, or that fits the decline rate of the transient quite well. And so this was shown to be consistent with being radioactively powered by heavy elements. And now, which heavy elements is still under debate about what heavy elements were really produced in this event. So we think that the neutron star mergers have a propensity to produce elements beyond iron, radioactive isotopes, which can power this event. Effectively, the radioactive isotopes produce gamma rays, alpha particles, and beta particles that become thermalized in the ejecta. And as they become thermalized, then effectively what we're seeing is a hot expanding ejecta, which cools, and it's effectively thermal radiation that we're seeing. Reprocessed radioactivity comes out as thermal radiation. But how much how much of the elements at the first peak, the second peak, or the third peak of the abundance profile are produced has not been well tied down yet. There are models of neutron star mergers which predict different amounts of these heavy isotopes. And you can see labeled here are the first, second, and third peaks. These are just peaks in the abundance profile, the known abundance profile of elements in the Milky Way and in the solar system. And there are peaks at these elements you can see here around mass number 80, around mass number 130, and up at the gold, platinum mass number around 190 or so. And so the expectation perhaps is that these more abundant elements could be produced in neutron stars mergers, and these peaks are reasonable places to start to look for elements that might be in the spectra of the kilonova. So there have been quite a number of detailed simulations of how neutron stars merge, what the ejecta is that they produce, nucleosynthetic calculations that estimate which heavy elements are produced depending on the composition of the material that's immediately ejected at the time of merger, and what the ratio is between the number of neutrons and the number of protons. So this is often labeled as the electron fraction because they're electrically neutral. The number of protons will equal the number of neutrons. Sorry, number of protons will equal the number of electrons, and that the ratio between protons and neutrons will set the pattern of production of the heavy elements. But it's often called the electron fraction. So there have been predictions that you can get material which is ejected from a wind around the merging neutron star, the one on the left here. And if that is mostly produced, if that mostly produces the first or the second peak in the R process elements, so around the strontium peak or around the barium xenon peak, then the opacity of that material is quite low, and you could get an ejecta which looks quite blue. It's also possible that both the disk wind and dynamical ejecta, which is material which is ejected as the stars, two neutron stars merge, and I'll show you a simulation of that. It's possible that if the neutron fraction is very high and the proton fraction is very low, that you can get the third R process elements produced. So that's the material around platinum, perhaps up to even beyond. So gold and platinum, osmium peak. So those heavier elements have many more electronic transitions in their ions, and they produce higher opacity material, and that would tend to be a redder component, and a component which would appear red or perhaps bright in the near infrared. And it could be a combination of these. There could be one, there could be two components, there could be multiple components, as demonstrated here by Dan Kaysen's work and others who have done these simulations and radiative transfer calculations to see what the material would actually look like. So what did we see with 170817? So the theory has suggested for quite some time that there may be multiple components ejected from a neutron star merger. It may be dominated by blue ejecta, low opacity. It may be dominated by red. And which of these components we see can give us constraints on what elements were produced. It's also possible that in between, so if you look in between the second and the third R process peak, we have a little bump here, which are the lanthanide elements. So they don't appear as abundant, but they may have a very strong effect on the spectrum because they have open F shells in their electronic configuration. They have lots of transitions, and so they've got produce a very high opacity, which means lots of the photons are trapped and they come out in the near infrared. So anything which produces lanthanides could appear to be very red or bright in the near infrared and faint in the optical. So there's reasons to search right across the infrared, the optical and infrared spectrum to see what was produced. So what did we see? Well, for sure, we saw a rapid blue to red transition in 170817. And here is an example, the movie on the left and the light curves on the right. So you can see the light curves on the right. There was really only one or two detections in the U band, and in the G band it faded very quickly. So faded very quickly in the U. It was detected with SWIFT and one detection on the ground. And then in the G band it faded within 4 days, 4 or 5 days to beyond detectability, even with large telescopes, 8-meter telescopes. But in the K band, you can see that it only peaked in its luminosity after about 4 days. So it became, the blue flux faded very rapidly and the red flux persisted for some time. You can see this with the movie on the left of all of the X-shooter spectra taken with ESO. Very bright at the start and look, that is just 2 days. It went from blue, very, very blue and hot inside the first 24 to 48 hours. It faded quickly and it became red very quickly, but the near infrared remained persistent for 4 to 10 days. And that was a very distinguishing feature of all of the data that were collected across many different observatories at the time. So can we make any sense of this? What elements were there producing this rapid blue to red transition? And can we model this in any way? Well, there've been several attempts to do this. I'm going to highlight some of our work, which will appear next year, which will be submitted and appear in the archive early next year by one of our students here at Queen's. There have been several attempts to do this. One attempt, the one of Dan Kaysen and his group and others have looked at trying to model all of the spectral energy distribution that we saw there from X-shooter. So modeling the blue deficit and the near infrared excess with a very broad range of elements. And they can produce the deficit in the blue and the near infrared excess, but without identifying specifically any particular element. Dara Watson has suggested that in the early spectrum, there is one feature in the early spectrum. It's around, you can see 7,500 here angstroms. It's a dip, a very strong dip in the early spectrum. He suggested that is strontium. Dan Kaysen suggested there are likely to be cerium and neodymium. These are lanthanide, heavy lanthanides. And he proposed that these were likely to be present given that the near infrared flux was so strong. But Dara Watson in his paper suggested this dip was specifically due to strontium. So If you want to try and model this, if you look at the periodic table, you have the question of where do you start? Which elements do you pick to try and make a model and a radiative transfer model to see if you can match any of these lines, any of the features that we observed? The difficulty, of course, also is the material is expanding at 0.2 C. So lots of the lines are blended together. So it becomes quite a difficult problem. And if you have many possibilities for the density profile, the temperature of the ejecta, all of these heavy elements, it becomes a very difficult multidimensional problem to try and constrain the elements that are produced. So the best thing to do is start with some calculations, first of all. So we've been working with Andy Boisfine and Stefan Gorley, and they take simulations like this, so hydrodynamic simulations of neutron star mergers, and they calculate what you might expect to find with different amounts of neutron fractions. And they produce different types of compositions that are produced from these neutron star mergers. Here are 3 examples. Lots of numbers here and lots of heavy elements, but I'll just point out these are 3 examples where, depending on the neutron star fraction, these realistic nucleosynthesis calculations produce lots of first peak elements, for example, strontium, that's in the first column. They can produce a blend of lanthanides where you've got 5% of the lanthanides, that's in the second column, and they can produce also with a different neutron fraction, a heavy element, an ejecta dominated by heavy elements, where the lanthanide fraction is nearly 30%, and you've got lots of platinum, quite a lot of gold, and osmium. So these should look very different, whether you're dominated by strontium and like elements or the very heavy elements. And these are realistic calculations based on those on the nucleosynthetic calculations. So what we did, and what James Gillanders, our student here in Belfast, has recently done, is that he's taken these realistic trajectories and he's put them into a radiative transfer code and calculated the spectrum that we should see from the kilonova. I'll just sort of skip over that and show you the results here. So the interesting thing is that what James finds is that you can't reproduce all of the spectra with one single composition. The early spectra do actually need an ejecta which is dominated by the light elements, and particularly strontium. So that feature at 7,500 does look like it's strontium. So we would support Dara Watson's result that is likely to be strontium. But as the object evolves, then we see specific absorption in the blue. And so these are the spectra here. The black is the observed X-shooter spectrum, and the blue is our best reproduction of that spectrum with a blend of lanthanides. So we require about 5% lanthanides to produce an absorption in the blue. Without lanthanides, you get the red spectrum here. And the red spectrum has lots of flux in the blue. Really, we need the lanthanides to depress that blue flux. So we think there's evidence for strontium, and there's evidence for both cerium and neodymium. They're the 2 elements that create lots of absorption in the blue. So actually what we find is I guess a blend between the early results from Dara Watson, who suggests that strontium is there, we would agree, and Dan Kaysen and collaborators' work, who suggest, yes, you do need the heavy elements, but we think we've specifically identified the regions in the spectrum which show that both of those must be present. So there has to be a different composite. The early spectrum needs to be only light elements, and then the later spectrum needs to be this lanthanide blend, but only about 0.5%. If you push the lanthanides up too much, you get a very red object. So that's, I think James will publish this work, we hope, early in the new year, which we think is a very comprehensive analysis of all of the spectra that were taken by X-shooter. And this is probably as much as we can extract at the minute from the spectra that we have for 1708-17. So that's I think as much as we can do with this this paper. I think will be our final estimate of what we think is contained in the ejecta. And we do need more objects now before we can constrain the what is produced in neutron star mergers overall. I'll just pause there before I go to what's coming up next and what we can expect next year.
Okay, thank you. Any questions? So I have one question regarding for these kilonovae models, are they like sensitive to the viewing angles, like in, just like, does that tells you anything about the geometry of the kilonovae or?
Yeah, that's a good question. So our radiative transfer models are spherically symmetric. They're not three-dimensional. The ones that we've applied so far. So the way we're dealing with that, and the merger simulations are obviously done in 3D, either 2D or 3D, usually 3D. So the way we deal with that is that we try and model the different epochs. If we require different compositions, then that may well be due to the viewing angle and parts of the ejecta which expand rapidly and then appear for a day or two, but have expanded so far that they're effectively gone or are not visible. So we can't reproduce the viewing angle dependence in 3D simulations yet, although there are codes which are being developed for that. But the way we do it is more in a much more simplified way to see if we are seeing evidence for a viewing angle dependence. So what we'd like to have, as I guess you're hinting at, is more of a 3D model. But you're absolutely right; it will depend on the viewing angle. Okay. And in this case, I think it's likely that we are seeing it probably toward from the pole.
So for the models you used to fit the 2017 at GFO, so which you didn't consider any viewing angles, right? Because you didn't use any, like you said here, the 3D models. Even for these models, you haven't really considered that. Okay.
Yes, that's correct. Yes, it's not a consistent 3D model for sure, and we're not looking at different viewing angles. That's correct.
Okay, we have questions from the audience here. Someone raise your hands, Chi-Hong, or do you want to speak up?
Okay, so can you hear my voice?
Yes.
Okay, so good evening. So I have one question. Is we know the different kinds of elements and it has a different masses. And if the masses is a different, the momentum also be different. So like for example, the Au, the gold, they are heavier more compared for the hydrogen or the Xa. So my question is when it's the neutron star or it's the supernova that exploded. So just like you see to be in a spectrum, inside it has a first peak, second peak, a different kind of element. So is it also possible that is it because when it's a complex missing element that to explode out, and a few times later because resistance keep the stable, but the masses and the momentum is different. So different kind of element, their speed is lower. Their speed also becomes different because the lighter element will be slower, faster. So maybe the hydrogen will becomes the slower, faster compared for the Ag. So after it's boiled a little time later, this kind of effect is also possibly to make Ag or heavier more the elements are first appear in the spectrum and produce the first peak because this is a most shortest for compared for our Earth, and the lightest elements will be in the back because they are far away compared in our Earth. Is that also possible? That's my question. Thank you.
So the answer to your question is yes, there can be layers of compositions, but it's not determined by the kinematics. So it's not determined by the it's not that it's a mv squared and that everything else is the same kinetic, everything is the same kinetic energy, and therefore the lighter elements move faster. It's determined by the neutron fraction. That's the overwhelming factor that drives the composition. So in the tidal tails, for example, so in this simulation that you see here, the material which is shot out now, so the material which you shot out is where the neutron stars first touch. And so that's going to be very neutron star rich. That's likely to be the heavy elements, so things like gold and platinum and osmium. So it's more the neutron fraction really drives the composition, not the initial mass of the mass of the nuclides. It's not the kinematics, it's the neutron star fraction, and that is definitely dependent on so that you can get layered compositions, but it depends on the composition and the amount of neutrons rather than the kinematics.
Okay, thank you so much, teacher.
Okay, we have another question from the chat box here. So he asked at the slide 10, number 10, wow. Your slide number 10. Yeah. Okay. Okay, so he's asking the curve from Livingston. Which one? Okay. Seems like the overlap. The curve of the Livingston. Can you see the question in the chat box? He said the curve of the Livingston seems like overlap of red and blue lines. Exactly what that overlap line is trying to say.
Oh yes, okay. The 2015 one. Yes, okay. So you can. So in Livingstone here, the blue is Livingstone, and the top right one here. So the blue is Livingstone, and it's just to show you that Hanford. If you take the Hanford one on the left and you overplot it on the right and shift it by the speed of light across the US, they exactly overlap. So it's to say, just shifting by the two detectors, because this, remember, this was the first detection. This was the claim for the detection of gravitational waves. There were some people at the time said, well, you can, maybe this isn't real, maybe it's a detector artifact. So they were pointing out that you get exactly the same waveform in both detectors at exactly the same time, just shifted by the speed of light between the two detectors, right? Because the wave hit one of the detectors first of all. So there is a time shift, and this also helped them to locate it on the sky. So it's the two detectors just overlaid.
Right. Okay, great. Thank you. Any questions? If not, I think we'll try to move. There's another one here. Okay, does the extinction or abundance of dust or gas in the host galaxy have a significant impact on the observations?
Yes, it certainly. So that will, and it's hard. It's usually hard to estimate. So there will be extinction along the line of sight from our galaxy, which is well known. The extinction in the host galaxy is quite difficult. Now that won't explain this object becoming very red, because that changed over time. The extinction should be constant. I think we assumed either zero or very small amounts of internal extinction in the host galaxy, but that will affect the estimate of the luminosity of the event. And we don't have a good handle on that. It's probably low, given that the first detection was very blue and there was a UV detection by Swift, so it's probably low, but the exact value is not well determined. Doesn't really affect the luminosity here that you see. It's probably around 10 to the 42, maybe a factor of a few tens of percent higher, perhaps. But it's probably not a big effect. Certainly does make a difference to the exact luminosity.
Okay. Yeah, I think especially for this case, 17 GFO, I don't think there's much extinctions from host galaxies, and there's some dust lanes. Yeah. There's some dust lanes, but I don't think it goes through the position of the kilonovae. Okay, thank you very much. Yeah, any other questions? Okay, one more. He says, naive question. What is the discovery rate of kilonova compared to supernovae?
Oh, okay. Yeah, nice question. So yeah, within it's about one to 1,000. So they're about the true rate of kilonova are probably about one. There's probably 1 kilonova for every 1,000 supernova within a fixed volume.
Yeah, it's very rare. Okay.
Yeah.
Okay, thank you.
Yeah.
Any more? Yeah, I think we should move on to your next part of this talk.
Okay. So the interesting thing then is how that question of what is the rate? What is the true rate of kilonova compared to supernovae? And so here's a compilation from Owen McBrien's thesis and ZTF, Igor Andreoni's latest paper, compared with the LIGO rate. So there's lots of estimates of neutron star, how neutron stars merge. So from galactic binary neutron stars, population synthesis, which is a theoretical estimate, short GRBs. If short GRBs are all from neutron star mergers, then what is the true rate? And we measure the rate in terms of the number per gigaparsec cube per year, which is usually the unit. You can see in blue below here. So here's the best estimate from LIGO at the minute for the rates of these are about 300 per gigaparsec cube per year. And it's uncertain by about a factor of 3. So the rates of these will really determine how much science we can do in this area in the near future. So I just plotted in the blue below, I plotted the big error bar, which is the big error bar is the latest estimate from LIGO. They're most conservative error bars for the true rate. And the thick blue rectangle is their earlier rate from the first part of 03. Interestingly, we've been searching for kilonova without gravitational wave detection, both ZTF and the ATLAS survey. We've been looking carefully for anything in the nearby universe, which is relatively faint in comparison to supernovae, but fades rapidly. And we have not detected a single object that matches 17 GFO. So it means they're rare. And so, but quantitatively, our error bars here on so two of them are upper limits, both ZTF and ATLAS, and they're both about the same, about 1,000. So LIGO, Virgo, Kagra estimate 300 per gigaparsec cube per year. And from the optical, we would say there's likely less than about 900 of these for 1,000. So that's I think that confirms that they are rare in the local universe. There aren't large populations of them out there, and the upper limit from LIGO Virgo it's not likely to be greater than 1,000 or a factor of 3. So this means within 100 megaparsecs, you expect about 1 per year, right? So this number here I've given in the table, this is the number of binary neutron stars we might expect in the next observing run, which is going to run for approximately 1 year. You might expect 1. And at a distance of 150 megaparsecs, which is what they estimate, LIGO, Virgo, Kagra estimate they can get out to 150 megaparsecs consistently through the run. So we might expect 4. This is my best guess for the next run, that we'll get about 3 or 4 binary neutron star detections that we can try and follow up. Now, the next big game changer is when there's an upgrade to LIGO and Virgo. This will come in about 3 years from now, so around 2025. This will be in their 5th observing run. And this is when the Rubin Observatory will be working as well. And I expect that they'll be detecting about 30 neutron star mergers per year. So what I think is going to happen in 04 is that we will see a few more events, but it won't be totally game changing. It'll be a few events per year so a few events within the 04 observing run. I'll be pleasantly surprised and very happy if that number is 10 and not 4, but I suspect it's going to be around 3, 4, or 5, given the rates that they know and given what our constraints from the optical surveys without gravitational wave detectors. So I think we're looking at about 4 in the next observing run. But the big game changer will be in 05, and that's when. So this is the timeline for LIGO, Virgo, Kagra. So the next observing run will be next year. in 2000 and starting 2022. I'll just redraw their timeline here because this was before COVID and before delay. So here's the true timeline now. So at the end of next year, 2022, this is where LIGO and Virgo will be. But the run will probably miss the start of the Rubin Observatory survey operations. They will likely start in 2024. But in 05, here's the big thing I think we should all be looking for. Beyond 2025, the Rubin Observatory will be working. The distance out to which we can detect these kilonovae will be, the neutron star mergers will be out to about 300 megaparsecs. The sensitivity of the LIGO detectors improve. Rubin comes online and is very much more sensitive to finding these than we have now. So we've only really got 1 to 2 meter telescopes, which are consistently looking for these. It's only really DESC, which is doing the dark energy camera, which is on a 4 meter telescope, which is a larger aperture than a 2 meter, which is more sensitive than these wide field small telescopes like ZTF and Atlas. The big jump will come in 2025, 26 with the increase in sensitivity by LIGO Virgo, and the Rubin Observatory will be online. It will have observed this whole southern sky. And if they decide to do TOO observations of gravitational wave sky maps, which is still not decided, this gives us a great opportunity to make to find very large numbers of kilonovae beyond 2025. So I'll just finish off showing you the capability of LSST and Rubin, and why this timeline of 2025 is so important. If you look at the typical GIY magnitudes of kilonovae at 300 megaparsecs, so this is where LIGO Virgo will detect most of their objects beyond 200 out to 300 megaparsecs. At 300 megaparsecs, these objects will be down and they'll be as faint as 22, 24 in between 24th and 22nd magnitude, depending on the 3 lines here, just different examples of ejecta masses. So out at this distance of 200 to 300 megaparsecs, you might be able to get the brighter ones with Pan-STARRS or DECAM. The fainter ones will be down in the LSST regime. So the red line and purple lines are the sensitivities of LSST. So really, once you get out beyond 200 megaparsecs, it becomes very difficult to detect these objects with our current facilities. And it's really LSST will make the next big change. It's the facility that will be able to detect tens of objects per year or per observing one. I don't think that jump will happen until LSST, until we increase the volume that we can detect the neutron star mergers within, and also have this facility, which is wide field and very sensitive. So here's an example an optimistic kilonova, quite a bright kilonova. This is an example of a red kilonova, one which has got lots of heavy elements produced and is therefore faint in the optical but brighter in the infrared. And you can see even at 200 to 300 megaparsecs, these are extremely faint. They're around 25th magnitude. So it's really only LSST will be able to detect these, because it's only LSST has got an 8 meter telescope and a wide field and totally dedicated to survey mode, and perhaps may use some of its time for target of opportunity. So I think I'm going to leave you with that. That really is the future. The rates of these objects are extremely important. Will define how this field will evolve over the next 2 to 5 years. I think the next observing run, and here's my conclusions here. The next observing run, it's all about the rates. If the rates are what we are as we expect, then we're likely to see only 3, 4, 5 perhaps neutron star mergers we're likely to see those 3, 4, or 5 detections. Then how many we detect with optical or electromagnetic counterparts is a question we will have to answer during the run. But the point I want to leave you with, it's not until 2025, when the sensitivity of the detectors, the gravitational wave detectors, reaches their design sensitivity, And we also have the Rubin Observatory working at the same time. It's only going to be in the southern hemisphere, but it will give us the sensitivity to detect these kilinovae. For example, the 1708-17 type objects, the AT 2017 GFO, that optical transient will be detectable out to 300 megaparsecs approximately, but only with the Rubin Observatory. So I think for younger people in the audience here and thinking of what are the projects you might want to work on over the next few years, I think this period is quite exciting. I think there's some uncertainty, and the uncertainty is mostly driven by the rates and exactly what these objects look like. It's probably driven by how frequently we can detect the counterparts. It's almost certain LIGO Virgo will detect several binary neutron star mergers and neutron star black hole mergers in 2004 next year. How many of those we detect with electromagnetic counterparts is uncertain. I think it's certain that we'll detect tens of objects per year beyond 2025. But what facilities we have that can follow up those and how bright they are and how sensitive our telescopes need to be is uncertain. So I think over these few years, planning a strategy and thinking about how to extract the information from the gravitational waves plus the electromagnetic counterparts is the challenge, and how we can maximize our chances of detecting the electromagnetic signatures, because it's really putting together the gravitational waves and the electromagnetic signatures that produces the exciting science. So I'll finish there. Thank you.
Okay, fantastic. Thank you very much. So any further questions for Stephen? So what about the space telescope? Is JWST going to contribute anything on this kilonova?
Yes, we hope so. So we have to find them first from the ground. So
Yes.
if we find a kilonova from the ground, I think there are four approved programs in the first cycle of JWST, which will nicely overlap with the next observing run. And JWST will be fantastic to map out the flux of these objects and their spectra, their spectral appearance between 1 and 5 microns. I think that's the key point. With no, and then of course there are no telluric absorption in this. You'll get a continuous spectrum with no telluric or Earth absorption bands in JWST. So, and I think even beyond 5 microns, seeing how much flux comes out beyond 5 microns is very interesting as well. So there are 4 programs approved to observe kilonovae, but we have to find them on the ground first. So JWST won't do any search for kilonova. The field of view is too small. But when they are found, then these programs will observe the event if it's confirmed. We need to confirm it from ground-based observations first.
Right, sure.
But very exciting to see what it's like, what the spectrum is like beyond 2 microns and out to perhaps 10 microns in the mid-infrared.
Right. Thank you. Any more questions from the audience? Okay, we have one here. What is the most suitable host galaxy to look for a kilonova? Spiral one, I guess. I mean, just from the audience.
Yeah, good question. I think two things that drive this. One, you'd expect stellar mass. That you'd expect them at some level, the kilonova to trace and the neutron stars to trace the stellar mass. So elliptical galaxies are also good candidates to host these. The big question is the merger timescale. So yes, neutron stars are produced in supernovae, and so supernovae do trace star formation. We've had almost certainly 2 supernovae to produce the binary neutron stars. So the question is how long does it take for them to merge? If it's a very long delay time, then elliptical galaxies, which have had large bursts of star formation in the past, are also good sources for these. So when people are doing catalog galaxy searches, so if you get a sky map which is small enough, you can pick out the biggest galaxies. And what people are thinking is to weight them both by mass and also some star formation as well, because we know type 1a, certain subtypes of type 1a supernovae seem to favor star-forming galaxies. So it really depends on the delay time, how long it takes them to merge after the neutron stars are formed. So it's both ellipticals and star-forming galaxies have the potential to be hosts of these. And I think it's an interesting question of what is the typical host of a binary neutron star merger. We'll only know that when we build up a sample of about 10, I guess, and see what their hosts are. But I think if you're searching, I would keep an open mind. I would not put in a galaxy bias at this point, because we don't know what that merger and delay time is.
Okay, so you don't have any priorities like prior host galaxy criterions, like something more massive or like
yeah.
Okay.
The first order, I would weight by mass. If I were selecting galaxies, which I thought were most likely to be counterparts, to host the counterpart, my first guess would be mass and then star formation rate. But I wouldn't make a decision on that. If I wouldn't weight them too differently. I mean, you'd probably go for more massive galaxies over dwarf galaxies, for example, just from a probabilistic argument. But we don't know, and so if you're searching for the counterpart and you're looking at particular galaxies, I would try not to have put too much bias on that.
Right. Yeah. Since we just have one,
Exactly.
we don't have a statistic sample or like what's their preference or. Yeah. Okay. Any other questions? Is there any discovery of kilonovae at high redshift, say about redshift larger than 5?
Yeah, so redshift greater than 5, no, but the highest possible. So for some of the short GRBs, so some of those have been observed after. If you get a short GRB or a long one, but the short ones, they all have afterglows. So you see the gamma rays, and then you see a rapidly declining afterglow, which is usually detected both in X-rays and in the optical and infrared. There is there are a small number of short GRBs where there's a claim there's a little bump in the infrared after 4 days, and that bump could be the kilonova. So the highest redshift one, I think, is 0.3, and that's probably the most convincing one. I think there was another one around between 0.1 and 0.3 are the highest redshift short GRBs, which have got an infrared excess. So nothing at redshift, beyond redshift 1, they're just too faint. The kilonova would be too faint to detect, but around redshift 0.1 to 0.3, it's possible you could detect the infrared excess in the H and K bands. And so there is one, Neil Tanvir has a paper, Ido Berger has a paper on this one, which is from, it's a few years ago, it was before 2017. There's been another 2, I think, since claimed to be potential kilonova. The difficulty is their afterglows fade rapidly and it's uncertain. And so when you detect something, is it the afterglow or is it the kilonova? And it's usually just a small number of data points. So they're plausible, but not confirmed. But redshift about 0.3 is the limit, I think, 0.3, 0.4.
Okay. Another question here. Do we have any observations, besides gravitational wave, optical, infrared, near UV, like microwave or radio follow-up for kilonovae?
Yes. So I no time to talk about this. This is quite an exciting area, an interesting area. I didn't have time to highlight this, but so this object was detected in the X-rays right through to the radio waves. Basically nearly every frequency we could observe it at. It wasn't detected by ALMA, but it was detected at radio frequencies and X-ray frequencies. And so they're almost certainly probing the jet, which produced the short GRB, and they are probing the jet interaction with, first of all, the ejecta material, and then the circumstellar, the circumstellar material around the neutron star merger. So it's not the sort of thermal kilonova that they that they probe, but it's the jet which is almost certainly formed from the GRB. So it's still being detected in the radio and the X-rays, and that's the jet as it interacts with the circumstellar and interstellar medium. So those are very exciting observations, and the fact we can detect it 4 years later is quite remarkable, I think.
Okay, great. Any other questions? Okay, I think looks like yeah. I think no more questions from the audience. Yeah, thanks. Thanks Stephen for such a fantastic talk, and it's been good. It's really nice to have you here, and hopefully, yeah, you can visit Taiwan at some point personally.
Yeah, I hope so.
Yeah. Okay. Thank you very much, and thanks for all the audience for joining us today, and everything is successful. Okay. Okay, Stephen, I'll see you next time.
Yeah.
Yep. Okay. Yeah. Bye-bye.
All right. Yeah. Thank you, Stephen. Have a nice holiday.
Yeah, thank you. I will.
Bye.
Okay, great. Bye.
Thanks, everyone.